calculate the angular momentum of a phonograph record rotating at 33 1/3 revolutions a minute. An LP has a radius of 15 centimeters, a mass of 150 grams. A typical phonograph can accelerate an LP from rest to its final speed in 0.35 seconds. What average torque would be exerted on the LP? It's kind of messed up that they give us L in this because that could confuse you, but not really the point. So what they give us is, you can see here, 15 centimeters. The change in time to get it to full speed is 0.35, and it's 150 grams. So we actually have quite a bit to work with here, which is great. And they're asking for the average torque that would be exerted on the record. I'm going to stop saying LP because, I'm going to say a lot of L's and a lot of everything. So record, not LP anymore. So our basic formula for that is torque is delta L divided by delta T. So we got to calculate the angular momentum first. So angular momentum is moment of inertia times this angular velocity or angular speed. Once again, I, moment of inertia, omega, angular speed or frequency, however you want to phrase it. You can phrase it in a lot of different ways. So we calculate omega by taking 33.3 revolutions a minute. I realize it's supposed to be repeating, but we're doing this for practical purposes. Multiply that by 2 pi, because once again, we want our answer in radians. And then we divide by 60 seconds to get the answer in radians a second. That comes out to omega equaling 3.49 radians a second. Now, I had to look this up, but a solid disk is calculated at 1/2 mass times radius squared. That's how we calculate the moment of inertia for a solid disk. There's a bunch of different formulas. I didn't quite realize there was that many different formulas for moment of inertia, but there are. But it's okay. We got everything we need to calculate that. So 1/2 times 0.15 times 0.15 squared, this being the mass, this being the radius, we come out with 0.00168. So now we have everything we need to calculate angular momentum. So we put all that in. 0.00168 times 3.49 equals 0.00588 kilograms meter squared a second. But remember, we're looking for torque. Referring back up here, torque being change in angular momentum over the change in time. That's time. I made that a little messed up. That's supposed to be a change in time. Apologies for my horrible handwriting. So, once again, we have everything we need. We have the angular momentum. This is our time, 0.35 seconds. So we divide that, and we come up with the total torque of being exerted on the record of 0.0168 Newton meters.